12.2 Ideal Gases and the Ideal Gas Law. An ideal gas. In an ideal gas, all entities have high translational energy, moving in randomly in all directions in straight lines. When ideal gas entities collide with each other, or with the container walls, the collisions are perfectly elastic. There is no loss in kinetic energy. The volume of an ideal gas entity is insignificant, 0, compared to the volume of the container. There are no attractive or repulsive forces between the ideal gas entities, and the ideal gases do not condense into liquids when cooled. Ideal gas is a hypothetical gas composed of particles that have no size, travel in straight lines, and have no attraction to each other, no intermolecular forces. The ideal gas law states that the product of the pressure and volume is equal to the product of the amount, the universal gas constant, and the absolute temperature. The universal gas constant, which is given the symbol capital R, is a constant value that will be found on your reference table, one that you don't need to memorize, but you do need to know how to find it. It's 8.314 kilopascals times liters per mole per Kelvin. Let's determine the amount using the ideal gas law. The Goodyear blimp has a volume of 2.5 times 10 to the power of 7 liters and usually operates with gas at a temperature of 12 degrees Celsius and a pressure of 112 kilopascals. What amount of helium does the blimp contain? And what is the mass of this amount of helium? Let's look at what's given. We're given a volume, 2.5 times 10 to the power of 7 liters, a temperature of 12 degrees Celsius, if we convert this temperature into Kelvin, we end up with 285 Kelvin. We want to find the amount. We know the temperature we know R is 8.314 kilopascals times liters per mole Kelvin. And we know the pressure is 112 kilopascals. If PV equals nRT, we can rearrange and isolate for N by dividing both sides by RT. So N is equal to PV over RT. Let's sub in our known values. That's 112 kilopascals times 2.5 times 10 to the power of 7 liters divided by 8.314 kilopascal liters per mole Kelvin times the temperature of 285 Kelvin If we punch this into our calculator, we end up with 1.1 4.18 times 10 to the power of 6 moles. We know that the number of moles is equal to mass over molar mass. So if we rearrange this equation, the mass is equal to the number of moles times the molar mass. The number of moles we found to be 1.18 times 10 to the power of 6 moles. And the molar mass of helium is 4.00 grams per mole. If we punch this in, we end up with a mass of 4.7 times 10 to the power of 6 grams. Therefore, the blimp contains 1.18 moles times 10 to the power of 6 and 4.7 times 10 to the power of 6 grams of helium. Let's determine the volume using the ideal gas law. Calculate the volume of 32.4 grams of nitrogen gas in a container at 25 degrees Celsius and 96.4 kilopascals. We're given a mass of 32.4 grams, a temperature of 25 degrees Celsius. Let's calculate that into absolute temperature. +25 plus 273 is 298 Kelvin. We know pressure is 96.4 kilopascals. We need to find the volume. But in this question, we're given the mass, and we need to convert the mass into the number of moles or entities of nitrogen gas. The number of moles of nitrogen gas is equal to the mass of nitrogen gas, 32.4 grams, divided by the mole of nitrogen gas, the molar mass of nitrogen gas. The molar mass of nitrogen gas is 28.02 grams per mole. So that gives us a number of moles of 1.156 moles. PV is equal to nRT, and if we're isolating for V, we're going to divide both sides by pressure. So V is equal to nRT over P. Let's solve. That's 1.156 moles times 8.314 kilopascals times liters per mole Kelvin times a temperature of 298 Kelvin divided by a pressure of 96.4 kilopascals. If we punch this in, we end up with a volume of 29.7 liters. Let's determine the density using the ideal gas law. Determine the density of 1 mole of pure carbon dioxide at STP. To find the density, you first have to determine the mass and the volume, because density is equal to mass divided by volume. First, use the ideal gas law to determine the volume. Volume is equal to nRT over P. We have 1 mole times 8.314 kilopascals times liters per mole Kelvin times a temperature of STP is 273 Kelvin divided by a pressure of 101.3 kilopascals. if we punch this into our calculator, we end up with 22.4 moles, or 22.4 liters rather. The volume of 1 mole at STP, as we kind of predicted, is 22.4 liters. Next, if we have the number of moles, we need to rearrange this to find the mass. Number of moles is equal to mass over molar mass, so the mass is equal to the number of moles times the molar mass. The number of moles is 1, and the molar mass of carbon dioxide is 44.01 grams per mole. So we get a mass of 44.01 grams. Now we can skip over these steps because we've included them up above. Determine the density of CO2. Density equals mass divided by volume. That's 44.01 grams divided by a volume of 22.4 liters. That gives us a density of 1.96 grams per liter. Therefore, the density of pure carbon dioxide at STP is 1.96 grams per liter. Deviations from the ideal gas law. Deviations from the gases occur because ideal gases do not really exist. Under ordinary circumstances, the differences between ideal gas behavior and real gas behavior are extremely small. Under high pressure and low temperatures, however, the behavior of gases deviates more significantly. So, at high pressure, real gases experience more collisions. This increases the attraction between entities. And at low temperatures, the gases travel relatively slowly. At these reduced speeds, real gas entities experience forces of attraction when they collide. Please read over this section, try any assigned problems, and any LMS quizzes on this section.